Okay, so this question is asking what is going to be the g acceleration at 5.8 meters. So this is what we're looking at. It is a sphere, whatever you can call it, a planet, whatever you want. And it has this hollow thing in here, so it's kind of like a donut. And the question is, we're asking what 5.8 out is, what the g is here. So our first step is to draw a Gaussian sphere, right? This will be our enclosed mass that we're trying to figure out. So we know the mass total, and we can set up ratio of our masses to volume. So our m inside this Gaussian sphere is going to be over the m total, which is given 2, 5, 2, 2, right? And that is going to equal our volumes. So what is volume of a sphere? It is 4/3 pi r cubed. So it's going to be equals 4/3 pi, and then r is going to be 5.80 80 cubed. And then you have to consider that this is empty space right here, so you have to subtract the empty space. So it's going to be minus 4/3 pi, and the r is 2, and that is cubed. So that is our volume inside this Gaussian sphere, and that is all going to be over our mass in total. So that's 4/3 pi, our r is 7.5, so 7.5 cubed. And then again, you have to subtract the empty space, minus 4/3 pi times 2.00 cubed. So once you do this, you can plug this into solver or simplify it whichever way you'd like, and you come out to m inside mass is going to equal 1140 kilograms. And now once you have your mass inside, you can find the g. So g equals our gravitational constant times mass over r squared, right? And we have all these numbers, and we can plug this in. So g equals 6.67 times 10 to the negative 11. That's our g, times m, 1140, right, over r squared, which is 5.80 squared. And this should come out to 2.26 times 10 to the negative 9. And you can use whatever units you like, but I like meters per second squared. And that is how to do a question like that. Okay, the next question asks a 100 kilogram white totaled Mercedes-Benz, tragic, is at an altitude of 2 times 10 to the 6 meters from the surface of the Earth. Find the change in potential energy, or delta U, and mass of Earth is given, and radius of Earth is given. So this question is pretty much testing the U, delta U, which is going to be equals negative G M E times the M of the thing. In this case, it's the Mercedes-Benz, so we'll just do M, and then it is over the radius, right, whichever one it is. And since it's delta, it's final minus initial. So U final, U initial. And then, yeah, you just subtract them. So we find what the radius at the final is and the radius in the beginning. So what can we do? We just plug the numbers in. So to first, we can do negative, right, because that's negative 6.67 times 10 to the negative 11 times the mass of the Earth, 5.97 times 10 to the 24, times our Mercedes-Benz, 100 kilograms, all over our radius final. Well, what is our radius final? It is going to be the radius of the Earth plus the altitude. So what is the radius of the Earth? 6.371 times 10 to the 6 plus radius or altitude, 2.00 times 10 to the 6, right? That is our first, that is final, and that is going to be subtracted by the initial, which is negative 6.67 times 10 to the negative 11 times, again, 5.97 times 10 to the 24. These stay the same, times 100, right, over, now this is where it's different, it's a different r. And the r is just the radius of the Earth, because at the initial, right, and then the car is here. So this is the altitude, we can do height, and this is the radius of the Earth. So final is all of that, initial is just this. So this is going to be 6.371 times, that's bad, sorry, 6.371 times 10 to the 6, and we can do this minus this, and you should come out to a delta U that equals 1.49 times 10 to the 9 joules. And that is how to do a question like that. Okay, and then this next question asks what the mass of these two identical orbiting stars are. So since they're identical, they have the same mass, and we are given that the velocity of them is this, and the time to complete one full cycle is this many seconds, which is, a lot. So our first step is to, if we want to find the mass, we should first find out the radius. So this makes a perfectly circular orbit right here, these two stars. So this, like right here, is the radius, or right here, they're all the same, right? So we can find this r. How do we do this? Well, we can set up an equation. Well, we know that the circumference, just from simple, geometry, equals 2 pi r, right? And we have, 2 and pi are constants. And then we need to solve for r, so how can we get the c? Well, what is c? Well, velocity equals, right, a meter per second, some form of that. And we have this. We have velocity and we have time. So we can set this equation up. 2.20 times 10 to the 5 equals our distance, which is c, right? That's one full rotation. And how long does it take to do one full rotation? It takes 1.24 times 10 to the 6. 1.24 times 10 to the 6, right? And then you can just multiply each side, and you should get c comes out to 2.73 times 10 to the 11. And then using that, you can set this equation up into this. So this becomes 2.73 times 10 to the 11 equals 2 pi r. Use numeric solver, solve for r, and you should get r equals 4.36 times 10 to the 10. This is meters. So now you have your r, and it is asking for the mass. So what can we do? Well, we can do the force of gravity is equal to centripetal force, right? Because this is a circular orbit, we can use centripetal force here. So Fg, well, what is Fg? That is g m times m, and it is going to be over our r, or the distance. And by the way, we're treating these as point masses, so they don't have like radii, so it just makes it simpler. And it is squared, right? And then Fc is just mv squared over r. So we can set these two equations up because we have most of the variables. So what do we come out with? So g, 6.67 times 10 to the negative 11, and then times m, right? That's just m squared, and that is over r squared. Well, we have to think what r is. So r is the distance between the two. So we found r, right? 4.36 times 10 to the 10. However, this r does not take into account the actual full distance this is. So we need to times the r by 2 to find the actual r, if that makes sense. So you should do times 2 times the radius, which is 4.36 times 10 to the 10, right? And that is equal to m times our velocity squared, right, which is 2.20 times 10 to the 5th squared over r, right, which is 4.36 times 10 to the 10. And by the way, this whole thing is quantity squared. So yeah, you can equate these and then you use numeric solver, and you should come out to m equals 1.27 times 10 to the 32 kilograms. And by the way, when you plug this in numeric solver, you know your answer is going to be quite large, so you have to plug in an estimate, your guess, as a really large number. Like for example, I plugged in 10 to the 30 and it popped out with 1.27 times 32. And if you plug in 0, it just will not give an answer. So that is how to do a question like that. Okay, and the next question is pretty simple. It is pretty much asking what is the v escape velocity? What is the escape velocity if you are trying to send a 10 kilogram object and is trying to escape the Earth's gravitational pull? So what that means is if you're asking for the escape, the escape velocity, then the final distance is going to be infinity, right? Because in order to be completely unaffected by g, you have to be infinitely far away. So this is what we're going off of. So what we can do is we can set up our kinetic energy is equal to our potential energy for this. So our kinetic energy is going to be 1/2 mv squared, and that is going to equal to our potential energy, right, which is a difference. So final, which is negative g m of Earth times m of the thing, and that is over, well, the distance, right? What is the distance? Like we said, it's infinitely far away, so the distance is infinite, minus our negative g, again, times m e times m over, and it's just going to be the radius of the Earth. So if we notice, we know that anything divided by infinity turns into 0, so this will just cancel out, and it'll be 0 minus a negative, so this becomes positive. So we get 1/2 mv squared equals positive, g, this is positive, g times me times m over re. Now we can plug in all these numbers, but if we realize the m's cancel, so what you really get is just v squared equals 2 times g times me over re, and you can just plug in these constants, which mass of the Earth constant, radius of the Earth constant, g constant, and you can solve for the velocity, and it should come out to velocity escape velocity equals 11200 meters per second, and that is for any mass object, because like we said, the mass really is irrelevant here. Like many things in physics, we can just cancel that out, and for any object it is this is the escape velocity. So yeah.